Great, fantastic. Well, so thank you all very much for inviting me and coming to the presentation. What I will present today is Project Malmo. Project Malmo is a test bed for AI experimentation, and it's a tool for asking questions about how to develop the future of AI. I'm sure one of the reasons that you're here today is that you are aware of the incredible progress that has been made in machine learning and artificial intelligence over the past couple of years. We now have machines that can recognize thousands of objects, that can recognize human language in real time and translate it to other languages. So it's a really accelerating period of time. And the key question is, how far can we actually push this? And how much progress can we make in developing future AI technology? Now, trying to invent the future is, of course, very complicated. So one of the key ingredients that is necessary is a tool that allows us to ask the right question. And that is exactly how I see Project Malmo. I see it as a tool for asking questions about where to take artificial intelligence. The first question, of course, is what is intelligence and what are we trying to solve here? And this is very much a question that is still very hotly debated and that we have no consensus on in the research community. My current working definition of intelligence is the one that Legg and Hutter proposed in 2006, and they proposed the definition that intelligence measures an agent's ability to achieve goals in a wide range of environments. Now, if we want to develop artificial intelligence, then I see two key components here in this definition. The first key component is this ability to achieve goals. So that implies having an agent that interacts with some environment that can interactively take in information, make decisions, and act in the environment in order to achieve its goals. There's also the second component about acting in a wide range of environments. So this is really about flexibility. It is about being able to develop an agent or an architecture that is able to learn to achieve a wide variety of goals and that continues to learn as it interacts with its environment. Now, these two components, flexibility and interactive decision-making, pose some key challenges in experimentation. So if we want to go beyond, for example, supervised machine learning towards agents that can actually interactively learn to interact with their environment, we need a new set of tools for measuring progress. This idea of measuring progress is what I see as fundamental to scientific research. In a wide variety of disciplines, we have seen that once the right tools were invented for measuring progress or observing new phenomena, we saw very rapid progress in those areas. And that ranges from astronomy to physics to a wide range of other disciplines. Now, in artificial intelligence, it's actually very hard to measure progress. As you saw, there is no agreed upon definition even of what we are trying to achieve. So it's even harder to come up with an idea of what to measure. As a approach to tackling this very, very, very hard conundrum, we are proposing to use a platform that allows us to very rapidly ask questions, test hypotheses, and in such a way that it allows us to start measuring progress in this area. Now, why is Minecraft such a fantastic platform for doing AI experimentation, for allowing this asking questions? I don't know how many people here are familiar with Minecraft, and because it's a little hard to ask this question remotely, I'll just assume that maybe half of you have kids who have played Minecraft, and maybe the other half has at least heard of the game. But just for those who haven't been able to play Minecraft before, it's an open-ended game where players explore, create, socialize. It's what's called a sandbox game that players enter. There's no predefined goal, so people can go in and play this game in whatever way they want. For example, one thing I like to do in there is just go travel to some mountainous region and watch a sunset. And I really like building tree houses in Minecraft. So you can really come up with anything that you want to do. This open-ended nature of the game makes it both very attractive for human players. It really allows people to be creative and explore new kind of worlds and new kinds of games. But it also allows us to build an AI experimentation platform on top of this game that presents an infinite variety of tasks that we can construct for AI agents. As a result of this allows us to take the platform we have developed, implement simple tasks that we can address using current technology, and then we can gradually build up the complexity towards environments that provide a huge amount of flexibility in terms of the tasks we want an AI agent to achieve. In addition to that, this world can be shared with other players, so we can easily generate environments in which human and AIs interact with each other. Both AI and humans can experience this world from a first-person perspective, and this allows us to develop agent technology that can learn to interact with a complex environment, including environments that they share with people. Now, what is needed on top of Minecraft? So Minecraft is already this fantastic game that provides this variety, but what was needed in order to unlock its potential for AI experimentation was an ability to very easily connect AI agents into this environment and to develop tasks that allow us to benchmark algorithms and reproduce others' results. Exactly this piece of connectivity is what Project Malmo provides. So Project Malmo is a platform for AI experimentation that is built on top of Minecraft to make it as easy as possible to construct experiments and integrate agents into this environment in order to develop new AI technology. In the next couple of slides, I want to briefly show two use cases on how to get started using Malmo for AI experimentation. And after that, I will briefly touch on the research challenges, or some of the research challenges that can be addressed, and some of those that we are currently addressing here in the team. So let's look at the key use cases and design principles that guided us when developing Project Malmo. As I already mentioned, we wanted to make it as easy as possible to connect AI agents into the game. There was an important balance to strike here between having an API that is powerful but also intuitive. And I think our team has done a fantastic job in achieving this. We also needed to provide researchers with the tools for creating tasks, building on existing Minecraft capabilities. And finally, the platform is built for extensions and novel users. As I already mentioned, the platform is available as open source online, so people can go and change it or extend it and adjust it to the needs they have for their particular experiments that they want to run. We made huge effort to make the platform as easily accessible as possible. So we are providing a platform that is cross-language. You can implement agents in Java, .NET languages, C, C++, Python, etc. And it's also completely cross-platform. So it runs on Windows, Linux, and macOS. Very briefly, Malmo consists of the following components. When you start up Malmo, you start up the actual Minecraft game. Inside the Minecraft game, there is a client-server architecture, and each agent would connect to one of the Minecraft clients. This is done via a mod that hooks into Minecraft, and the mod is really key to exposing the state of the Minecraft world to the agent and getting back the commands to send to the Minecraft world. So on top of this mod sits the API that the user code actually interacts with, and this API would be called to get observations about the environment, etc. So let's look at two simple examples of how to use Project Malmo. So this is really the 101 tutorial of how to develop agents in the Minecraft world using Minecraft. The fundamental idea is that we want to have an agent that interacts with the environment, and we can think of this interaction as an interactive loop. If you're familiar with reinforcement learning, this must look very, very familiar to you. Very briefly, an agent interacts with the world by taking actions and then observing observations and rewards about the environment. So in this way, we can abstract all situations where an agent takes an action, then observes the consequences of its actions and tries to learn from those. Now let me show you what this looks like in Python. So here we have a very short setup where a very simple agent would enter a basic Minecraft world. And as you can see down here, it is interacting with the world while the world is running. It is collecting some rewards and observations, but for now the agent will just ignore those rewards and observations, and instead it will just move, turn, and jump. And there you go. Very, very easily you have an agent that moves, turns, and jumps in a plain basic Minecraft world. Now, of course, well, jumping is only so much fun when there's nothing to jump over. So let's look at how to actually create a task to make this environment a bit more interesting. There are two ways in which researchers can create tasks in Project Malmo. The first one that we take as recommended is using a mission XML file. And the key idea behind using this programming language independent XML file is that this should make it easy for researchers to exchange their task setup. So let's say someone runs experiments with a specific task that is defined in an XML file, then we can simply exchange this mission definition XML to enable others to run their agents on the same task. And this is what I focus on in this talk here. I've abbreviated the XML here a little bit to just cut to the key ingredients that that allow us to turn this into, for example, a task for a reinforcement learning agent. The key ingredients here are what's called the agent handlers. And for each agent that interacts with the environment, this agent handler allows us to specify what observation the agent should get from the environment. So for example, does the agent see purely the pixel frames from a first-person perspective, or does it get a more symbolic view of the world, or should it additionally get, for example, chat messages so it can communicate with other agents? So this is the observations, what the agent sees about the world. In addition to that, we can specify an action space. So we can allow agents to move either in discrete or continuous space, and this is important for connecting, for example, to certain parts of the reinforcement learning literature. Finally, we need to specify the reward structure. So in the setup that we have chosen, the researcher can associate specific rewards with a wide variety of conditions in the environment. So for example, there could be negative rewards for taking steps in the environment or for taking an action. There could be positive rewards for collecting certain items or for finishing on a goal block. So in the example here, we see a basic implementation of a canonical task in the reinforcement learning literature. It's called cliff walking, and it's based on the cliff walking task in the Sutton and Bartow reinforcement learning book. The task here is quite simple. An agent starts on a starting block in a cliff that is surrounded by lava, and the goal is to have the agent navigate to the blue goal block at the end. So if the agent touches the goal block, it gets a positive reward. If it dies in lava, it gets a negative reward. And there is a small per step negative reward to encourage the agent to find a short path towards the goal. Now, from these simple components, this ability to construct tasks using the simple XML language, combined with the power of the Minecraft game, we can construct an infinite variety of different AI tasks. And this opens up key research challenges. In the next couple of slides, I will give a very, very brief overview of some of the starting points for doing, for example, reinforcement learning research using Project Malmo, and then I will provide some pointers to some of the work that we're currently doing. Right? So you have just seen this very simple cliff walking task, and I was mentioning that this is one of the canonical tasks in reinforcement learning. There's also a very effective solution to this particular task, and it's called Tabular Q-learning. And this example is provided with the Malmo platform. So if you check out the Malmo platform, you can actually go in and try to run this and have an agent that learns to navigate to the goal block very quickly. The idea here is that the observations that the agent receives are a tabular representation of the environment. So in the view on the right, in the Q, you can see an illustration of what's called the Q table, a representation of the states that an agent has explored so far, and its estimated value of taking an action in a particular state. So you can see for the starting state, when the agent has just started to explore its environment, it may know only a single state, and so far it maybe has learned that walking forward from the start block is a bad idea, it gives negative reward, and walking off to the sides, maybe it doesn't have, it hasn't collected much information yet. So the key challenges in reinforcement learning are that the agent needs to not only learn about how to, what actions are useful in its environment, it also needs to explore. So only when it reaches a block next to the goal block can it actually explore which action is a promising action in that particular state. So a key challenge is balancing this exploration of learning something new with exploitation of what the agent has already learned. We can see here in the example that we have implemented here, we are using tabular Q-learning with epsilon greedy exploration, which means that some small portion of the time the agent would take an action at random, and the remainder of the time it takes the action that it judges as the most beneficial so far. And this simple algorithm allows the agent to continuously learn about its environment. You can see all the way on the right how the agent has already explored a larger part of its environment, and it's slowly learning about the reward structure that is associated with taking actions in this environment. And now if we run this algorithm for about 10 minutes, we successfully train an agent that navigates this environment all the way to the goal, as you can see over here. You can also see on the left there that the Q table, the representation that the agent has learned, has evolved or has been updated so that the most promising states have the highest reward estimates in accordance to the rewards that the agent has actually perceived. And it's really key to this algorithm to propagate information about rewards collected on future states back to the earlier states so that the agent actually finds a path to a promising goal state. Now, a key limitation of algorithms with tabular representation is around generalization. Now, on the one hand, these algorithms can be very effective. So, for example, if I can give a suitable representation for solving a given task, such as the tabular structure here, I can get an agent that learns to achieve this task very, very quickly in about 10 minutes of learning or about 100 episodes. However, as those tasks become bigger and maybe there are certain regularities that could be exploited for learning, the agent wouldn't be able to generalize over that. It would have to explore from scratch in every new state that it encounters. This ability to generalize was what's key to the success of deep reinforcement learning that has been so impressively demonstrated over the past 2 or 3 years. For example, in solving Atari games or learning to play Atari games at human ability. And we can apply similar algorithms here in Project Malmo. So here I'm showing an example of applying deep reinforcement learning to this task of navigating this room with some lava to successfully navigate to the beacon shown in the top left corner of the screen. What I'm showing here is a screenshot where an agent has already learned to navigate this environment, and you can see a representation of the Q values where it can judge that taking a forward action, taking a forward move when it's facing lava is a bad idea. So to just this, here's an agent that has learned to actually look around itself to collect the right visual information that allows it to navigate to the goal. And with generalization using deep neural networks, we can ensure that an agent can successfully find its way even when the configuration of lava is changing, something that wouldn't have been possible using, for example, tabular approaches. Now, with deep reinforcement learning, we have seen that agents can successfully generalize even in complex environments using only visual information. A key limitation at the moment is that these approaches take a huge quantity, a huge amount of data to learn effectively. So for example, in the example I just showed, it requires about 1 million to 1.5 million steps in order to learn to successfully navigate to this beacon. If we were to look at a single individual task, something like tabular Q-learning could learn this much, much faster. So a key open challenge is to understand how we can develop more data-efficient approaches to deep reinforcement learning so that we combine the power of learning to generalize with this ability to learn quickly in a relatively new environment. Some preliminary work that we have done in this space was looking at so-called multitask reinforcement learning. The intuition here was that in Minecraft environment, we are able to construct tasks that are very closely related to each other. And this allows us to test hypotheses about how the similarity between tasks allows an agent to learn tasks jointly and to generalize. What we found here was that with multitask reinforcement learning on related tasks, the agent is actually able to learn as fast or even faster than learning single tasks from the same amount of data. More interestingly, we found that the agents learn shared representation in this multitask setting. So in this figure here, I'm showing data that was collected using 2 tasks that have been learned with a multitask RL setup. In one task, the agent had available actions where it could turn and move forward. And in the other setup, it could walk north, south, east, west without turning. The different tasks here are highlighted in red and blue, and we can see that the clusters that emerge from projecting this representation in a 2D space are tightly intermingled. And actually analyzing this representation, we see that there's one distinct cluster that emerges when the agent faces danger, so when it's looking at lava. So we have a first suggestion that with multitask reinforcement learning, the agent can actually learn semantically meaningful representations for given tasks. Now, this was only a brief starting point, and what I'm really excited about with Project Malmo is that it gives rise to a variety of research directions. It is really a sandbox that allows us to ask new questions about AI, and it allows us to push forward the state of the art. A direction that I am particularly excited about is this ability to have AI agents and human agents in the same environment. And this gives rise to new research challenges around learning to collaborate. And in the long run, we hope that this platform will give rise to agents that learn to successfully collaborate with humans. This is something me and my team are currently hard at work on. We will actually be looking at releasing a task and samples that will push research in this direction. So stay tuned for updates on Project Malmo. And in the meantime, I would like to encourage you to try this out for yourself. Project Malmo is freely available on GitHub, and there's a huge variety of examples. If you look at the Python samples, you can learn about reinforcement learning, tabular approaches, and you can also look at how to try to improve some of the current reinforcement algorithms that are already out there. Thank you so much for your attention.
En fait, what we're going to do, oops. Qu'est-ce qu'il est le...
Tu cherches quoi, Igor?
J'aimerais en fait virer ce... J'aimerais aller ici et enlever le... Je voudrais enlever ça en fait.
Attends.
Tu peux ici, s'il te plaît? Voilà, enlever ça. Voilà. Okay. Yeah, I'm sorry. So we're going to have to ask the crowd to essentially applaud the second time. Katya, you can put your face on so that we can actually see you. And then afterwards, we can essentially get the micro around and ask if anybody has any questions.
Pour le moment, non.
La première question est la plus difficile. All right.
Thank you, Katya. Just one question. Is it possible to specify the policies in your API?
Is it possible to specify the policies in your API?
To specify the policies. So the way it is shipped is that the experimenter would develop the agent. So an easy way to get started in specifying a policy would be to take one of our example agents, for example, the Tabular Q-learning agent, and in there you can construct or provide the policy in any way you would want.
Okay. Another question for Katja.
Une autre question?
Don't be shy.
On peut traduire, hein, ceux qui vous pouvez poser la question en français. Ceux qui ont un
Vas-y.
problème de.
Vas-y, c'est quoi la question?
Hello, I wanted to know, I don't know at all reinforcement learning.
Okay, you don't know anything about
So
the
just a question,
Yeah.
how the algorithm is initialized. Just for the agent,
Yeah.
what will be in a simple way, what will be the action, what will be, how the agent will be initialized in the, at the first, at the beginning of the algorithm.
The cold start.
The cold start.
How it's initialized, right?
Yes.
Right.
So in the tabular Q-learning, the agent is assumed to learn from tabula rasa, so to not know anything about the environment. Different initializations of the Q table that I showed would give rise to different learning speed. Typically, we just initialize all the values to 0, and then the agent has to start to learn and update those values according to its experience. But learning could be sped up if we have prior information. We could put that information into the initialization, and that could help speed up learning.
Okay.
Il n'y a pas un Tony Parker qui veut récupérer le micro? Non?
All right, Katja, I got a question for you. DeepMind, DeepMind and OpenAI came up with different words and essentially video games, a bit like Minecraft. What is the main difference between their approaches and what you're proposing here on Project Malmo?
That's a fantastic question. I'm actually really excited to see the new experimentation platforms for AI that are coming out, both from DeepMind, OpenAI, and other groups as well. Each of those environments has a different view of AI and where it should be going. And this is reflected in the kinds of tasks that people are selecting. So for example, a lot of the DeepMind tasks are very focused on physically accurate interaction with the world. So it's really about learning physics, for example, and learning to interact with the physical environment. Something that I'm particularly excited about is, as I mentioned, this ability to learn to collaborate with other agents, including humans. And this is what we focus on here. So we take a middle ground between something that would be physically accurate and something that is very high in the complexity in terms of interactions between agents.
Okay, and any word on the other environment? You were mentioning essentially that DeepMind had one. What do you think is the focus for OpenAI, or at least what you understand from what OpenAI is opening up?
As far as I'm aware, the motivation between the release of Universe is really this push to flexibility. So having an agent that can perform tasks in the greatest possible variety of environments. This flexibility is something that we have discussed, of course, as well. One thing that is particular to the Malmo environment is that in Malmo, we have a single coherent world with coherent physics, and all the different tasks that can be implemented there underlie similar physics and similar regularities in this environment. This allows us to do experiments that would allow agents to build up common sense knowledge and then apply that common sense knowledge to new tasks that come up in this environment according to the same coherent structure. In Universe, this flexibility would be more generic. So you would try to push towards more generic problem solving rather than this ability to learn common sense knowledge.
Great. Another question, since nobody's really raising their hands. at some point in time, you want Project Malmo to learn about interactions with others, learn the rules within a certain world. Where does it bring us?
I hope that the long-term potential of AI is that we can develop new machines, new algorithms that help us achieve more, that help us achieve our goals. So in this sandbox, I want to explore how this new collaboration can be enabled.
Okay. And in terms of metrics, how do you go about publishing a paper on doing fantastic things on Project Malmo compared to another paper that has also beautiful things on Project Malmo? What's I know for the classification, you just do a better score on classification on ImageNet and whatever. In those type of words, where is the metric? Who's setting it up? And all the questions that are linked to that.
That's a fantastic set of questions, and it's a set of questions that we're still very actively working on, both here in my team and in the research community. As you mentioned, for more general AI, there's no agreed upon metric, as similar to the fact that we don't have an agreed upon definition of what AI is. So what I hope to enable with Project Malmo is that people can propose tasks that they consider challenging or interesting, or that push agents, for example, towards this flexibility of learning. Then people can propose those different sets of tasks, and we can evaluate them as a research community. We can see whether pushing in this direction is actually the right direction. I think this will very much be an iterative process, with tasks being proposed, revised, and step by step, we can make our way towards greater understanding of the fundamental challenges and how to solve them, rather than single-mindedly optimizing for a single metric, even if it's not necessarily the one that we actually want to make progress on.
Okay. Any other question? One last one? Yes.
Hello, Katya. To continue on the subject, you are mainly saying that people are going to propose new tasks. Is Microsoft going to move in the direction of giving a set of tasks? Not a long time ago, Facebook just released a set of hierarchical, it's a hard English word to say it, hierarchical set of tasks for transfer learning, and an environment, a very small environment with it. I think, as you said, Minecraft could be very, very awesome for transfer learning on different set of tasks. And so is Microsoft going to pushing also in this direction, or are you going to wait for the community to move on tasks and complexity?
So just let me repeat the question to make sure I understand correctly. So you're asking about transfer learning and whether Microsoft is working on releasing tasks for specifically transfer learning. Is that right?
Exactly.
Yes.
Right. So at the moment, my team is focusing on collaboration. So I think the first task that will come out will be in this space. I am discussing with a lot of academic partners on how transfer learning tasks could be set up. There are a couple of unsolved fundamental challenges in how to set these tasks up, because if the experimenter knows the tasks ahead of time, we can put a lot of bias into our agents that allow them to learn very quickly on the particular set of tasks that we have designed. But that doesn't necessarily allow us to test this very generic ability to transfer knowledge from one task to the other. I don't have a very good solution to those challenges yet. If you have any suggestions, I'd be very curious to hear from you. Other than that, we'll continue those collaborations, and hopefully we'll be able to come up with a good set of tasks in the future.
Well, thank you, Katya. Well, let's applaud Katya a second time.
Thank you so much.